This is section 3.4, linear regression. Okay, regression lines. Okay, in the previous section, 3.3, we looked a little bit about trying to get the best line to approximate some data. Remember, anytime you have just 2 points, it's exactly linear. So with 3 or more points, it can still be exactly linear, approximately linear, or not linear at all. So in experiments and observations, there can be small differences in what we record and what really happened. So it's like the predictions are what we record, and what really happened is what we actually observe. So we usually try to find a mathematical model, which means a mathematical function, that will explain the data. And of course, in this section, we're looking at our models to be linear, the y equal mx plus b, or f of x equals mx plus b. So the mathematical model is supposed to predict or estimate the values of the dependent variable. And again, the idea is they estimate or predict. They may not be exact. It comes down to, were our data exactly linear, approximately linear, or not linear at all. So each value of the independent variable will have an actual or observed value of the dependent variable and a predicted or estimated value of the dependent variable that comes from the mathematical model. Remember, the mathematical model predicts or estimates, and the actual or observed value is when we actually do the experiment, and what do we see. So we introduced the following notation for each value of the independent variable x sub I. So remember, there are going to be a total of xn data points, so I would go from 1 out to n. So for each one of the x's. Now that's a colon there, in case you're wondering what are the two dots. That they're not part of the xi notation. It's a colon. So y sub I is the observed value of the dependent variable. In other words, we actually perform the experiment, or it's what is in our table of values. The y high with this y sub I with this little circumflex on it is called y I hat. It's called, so without the I, it's just y hat. It's the predicted or estimated value of the dependent variable. Okay, so it is what comes from the model. Okay, so the one with the hat, it comes from the model. The one without the hat, it's actually in the table, or what we actually observed when we did the experiment. Now, note again, the yi comes from the experiment, yi hat comes from the mathematical model. So with web notation, we're going to make the following. Definition. It's a two-part definition. Number 1 says, the difference between yi and yi hat, which is yi minus yi hat, is called the deviation between the observed value and predicted value. So the deviation is observed minus predicted. Okay, so deviation, remember, it's observed minus predicted. Number 2, the square of the above value, which is yi minus yi hat, is called the squared deviation between the observed value and predicted value. Now, there's a reason why we look at the squared deviation. One reason is to take care of in case you accidentally subtracted backwards. When you square it, whether you subtracted backwards or not, you get the same result. Another one is actually purely mathematical in nature. It's how we measure things in mathematics. Again, in terms of squaring stuff, think Pythagorean theorem. You know, a squared plus b squared equals c squared. So there is always a deviation and a squared deviation for each observed and predicted value. And when we calculate them, we usually do it in a table. So remember, the deviation is observed minus predicted. Okay, the squared deviation is a measure of the distance between the observed value and predicted value. Now again, the reason for squaring deviations is mathematical and statistical nature. But it does correspond to how we measure distance between 2 points on the plane. And again, think the Pythagorean theorem. The a squared plus b squared equals c squared. So definition. The sum of the square deviation is called the sum of square deviations, just like its name sounds. It is usually just called the sum of the squares. Okay, so you add up the squared deviations. Remember, the squared deviations can never be negative. So when you add up the sum of the square deviations, it can never be negative. The worst it can be is 0, which if it's 0, that means that the observed value and predicted values were all the same, which actually is kind of great. That also means that in terms of linear models, that means your data were exactly linear. So when trying to find the best mathematical model for a set of data, it is common practice to choose the one that minimizes the sum of the squares. You want to make the sum of the squares as small as possible. And again, the smallest it can be is 0. So the smaller the sum of the squares, the better the model is. Definition. Again, we got a two-parter. Number one, the linear model that minimizes the sum of squares for a set of data is called the least squares line or the linear regression line. Anytime you see this word regression, it always refers to minimizing the sum of the squares. Number two, in general, any model that minimizes the sum of squares for a set of data is called the least squares model or the regression model. Now, our calculators can actually calculate the regression models. We don't have to go through all the nasty mathematics and statistics to figure out how do you actually determine these regression models. That can be rather cumbersome and time-consuming. For us, the time-consuming part is giving the data to the calculator. Now, we want to find regression models. In this section, we're going to be doing linear regression. It is appropriate to use linear regression for exactly linear or almost linear. But now remember, you can use linear regression if the data is not linear at all. It's just that it won't be a very good model. So, finding equations for regression lines. We're going to illustrate how to find equation for regression lines on the calculator with a specific example. So recall that a line has equation y equals mx plus b. Now, for some reason in the calculator uses either y equals ax plus b or y equals b plus, that really should say ax. For some reason the calculator always calls slope a. I don't know why, but it does. So I'm going to prefer the y equals ax plus b, but if you use this one, you get the same values for the y-intercept and the slope. Okay? So again, that should be an a, not an m, because the calculator always uses a for slope in the regression models. So here's our illustration. Okay, we're going to find the least squares line for the following data. So our x's are 3, 6, 9, 12, 15, and 18. And our f of x is 1, 10, 19, 28, 37, 46. Now, even though all the x's are the same distance apart, in order to get a least squares model, they don't have to be. It's just kind of convenient when they are, but they don't have to be to do the least squares models. So step one, we first enter the data using the stat key. Recall from the previous section that the x values go into L1, which means list 1, and the f of x values, the y values, go into L2. Okay, so let's do that. So we take out our calculator here. Come on. So let's see. Go stat. We're going to edit. Anytime you're entering data, it's edit. Okay, and L1, 3, enter, 6, enter, 9, enter, 12, enter, 15, enter, 18, enter. So we've got our x values in. Scroll to the left to go to the L2s. So those are the y values. So 1, enter, 10, enter, 19, enter, 28, enter, 37, enter, 46, enter. Okay, I've got them all entered, hopefully correctly, and then quit the screen. So quit. Okay. So that's our step one. Step one is the time-consuming step, entering the data into the calculator. Okay, so there I've entered the data into the calculator. And again, you might want to make sure that you actually did it correctly, because if you didn't do it correctly and you let your calculator do all the work, of course your least squares line is not going to be correct. Okay, step two, press the stat key. Okay. So you're going to get that. Now, we're actually trying to do some calculations, and that's what the CALC stands for. So step 3, use the arrow keys to navigate to calc, which means calculate. So you use your left navigation key to highlight calc. Okay. Now we have all of these things. Now again, notice choice 4 and choice 8 are linear regression. That's what the LIN stands for, linear regression. You notice there are several others as well. Again, I'm always going to use number 4, the AX plus B. So we want to use linear regression to match our usual slope-intercept form of y equals x plus b. We choose choice 4. Okay, so when I press 4, so let me get caught up all the way on my calculator here. So stat calc. I'm going to press 4. Okay, and I get this menu. Okay, again, the x's it says in L1, the y's are in L2. Remember, that's the default. Okay, the frequency list, you don't need to worry about it. And this choice right here, it says store regression equation. That's in case you wanted to graph it. This way you don't have to key in numbers or anything. It'll automatically put it into whatever y location you want to put it into, y1, y2, whatever. So, again, there's our result of pressing the linear regression of ax plus b. Okay, everything should really be okay except that if you want to store the linear regression into one of the y's, y1, y2, so you can graph it later on. So after verifying that everything is correct, which they are, L1 is the x's, L2 is the y's, we're going to scroll down to calculate and press enter. I'm going to store the equation in y1 so that I can graph it later. It might be kind of fun to look at. So you're going to scroll down to store equation, okay, and you're going to press enter. Okay, now I'm going to put in the y1 by using the vars menu. So to actually go through all that, so scroll down to frequency, so vars, yvars, function, and y1. Okay, now notice the cursor is not completely dark, it's kind of a gray thing, so this is telling me that I'm going to store the regression equation in y1. I won't have to key in the coefficients or anything. It does it all automatically for us. So if you get caught up where I am, so I got that. And it says scroll down to calculate and press enter. When you do that, you get this. So a is 3, b is negative 8. So the regression equation is y equals 3x minus 8. So again, let me get caught up here. So scroll down to calculate, enter. Okay, notice the screen kind of flashed a few things going on there. That's kind of like what the calculator is thinking about. Now, if you check your y equal, you should see 3x minus 8 for y1, because remember, that's where we stored it. And see, there it is. Now, it put plus minus 8, but remember from algebra, plus minus 8 really is minus 8. So if we wanted to graph stuff, we're prepared to graph it. So the least squares line is y equals 3x minus 8. Again, don't put plus minus, it's minus 8. So to graph the equation and the points, I use the following window. Because remember, we could look at the table of values to get our maxes and mins. So let's go ahead and graph it just for fun. So let's go ahead and set the thing up again here. So window, x-min is 0. The x-max, I'm using 21 for some silly reason. And for my scale, I'm using 3. Oh, I remember the data were all 3 apart. That's why I did it. And then let's see. The y-min, we're saying 0. Okay, the y-max, I went to 50 because I believe the highest or the largest y value is actually 46 or something like that. And I'm having as my scale 5. And now remember, I've got some data, those points, those L1 and L2, so I would like to graph them as well. So I'm going to have to turn on the statistical plots, one of these statistical plots. So let me get out of the window menu here and do second stat plot. And I'm going to turn on number 1. Okay, so enter, and then just turn it on. Okay, remember, by default, the first one is going to be the dots. So now when I graph this, I should see the dots. I should also see the regression line, the y equals 3x minus 8. So let's just graph away here. Okay. Notice the line went through each one of the dots. That means this data, they are exactly linear. So if I get caught up here in the slides, okay. So we have exactly linear data. Remember, if you wanted to have the grid lines on, you go to press second format and just turn the grid lines off. So if I do it on the on here, if I do it on the calculator here, so let's see, second format, the grid. Let's have lines. I hate the dots. Enter, and let's graph again. Again, notice the least squares line passes through all of the points. So this shows that the data are exactly linear. So we're going to look at some examples now that we see how to do it. So our examples. Okay, number 1 says, given the following data, so there I have my data. Part A, find the linear regression equation. Part B, use the regression equation to estimate f of 6. Number C, does the regression equation overestimate or underestimate the observed, that should say observed value, not observes value, so observed value of f of 6, and by how much? So there are actually 2 questions in C, like, overestimates by 2.7 or underestimates by 2.7. And part D, use the regression equation to estimate f of 7. And, if necessary, round all final calculations to the nearest hundredth. Notice, if I wanted to do f of 7 from the table, I'd have to go back to all that stuff that we did in Chapter 1, get your average rate of change, count how many values there are between 6 and 7 and all that stuff. So if I were doing that way, my table should give me a value of somewhere between 4 and 5. It'll be interesting to see whether or not the regression equation does that. So again, if necessary, run all final calculations to the nearest hundredth. Now, we're going to let the calculator do the calculation of the linear regression line. Okay? So, our solutions. Okay, since we're supposed to put this into our calculator, let me first clear out all that other nonsense. So, let's quit this. I'll quit. Let's get rid of my y equals. Clear it out. I may not have to graph it, but let me put my Windows setting back to standard. Okay. Now notice I still have a few data points there, so I got to get rid of my lists. So second plus for the memory, and choice number 4, clear all lists. So 4, and press enter. It's done clearing out the list. So if I didn't clear out the list, I would see the previous data when I started to do my stat thing. So let's clear that. So I'm going to set my float to 2, because remember, nearest hundredth. So let's go ahead and do that. Mode, and we're going to float on over to 2. Press enter, and quit this. Okay, you're going to enter the data into the calculator using the stat menu. So let's go ahead and do that. Okay, so stat, just press enter because we're already editing. Okay, remember we last did L2, that's why the cursor is still there. So scroll back to L1. Okay, so you got 0, enter, 3, enter, 6, enter, 9, enter, 12, enter, 15, enter. Okay. Now remember, it's putting the point 0, 0 because we set our float to 2. So now let's do the y values. Okay, so -1, enter, 2, enter, 4, enter, 5, enter, 9, enter, 11, enter. Whoops, enter. So we have all of our data into the calculator. So quit. So there we have it. Now, even though I said I set my float to 2, evidently I didn't in my data there because you don't see the point 0, 0. Okay, now we're going to quit the screen. You're going to do the following. You're going to go Stat, Calc, Choice 4. And you get that. And because we're going to make some calculations in some of the other parts of the question, like in Part B and D, let's go ahead and store the regression equation in Y1. So let's go through all that. So Stat. My cursor is not wanting to work with me. Calculate. Choice 4. Okay, my lists are right because I put them in L1 and L2. The regression, again, we're going to store it in Y1, so do vars, yvars, enter, Y1, okay, and then we calculate. So we got A is 0.78, B is negative 0.86. So again, I put my Y1 for the regression equation. Okay, I got the same result that we just looked at. So for part A, the regression equation is y equals 0.78x minus 0.86. That's your regression equation. Okay, again, coming back from right here. Okay, part C, the regression equation gives f of 6 as this. Okay, so remember, we've got it stored in y1. So I can quit this, do vars, y vars, enter, enter, and I want of 6, so 3.82. Okay, 3.82. So the predicted value for f of 6 is 3.82. Now if we go back to our table to find out what did the table say, the observed value for 6, the observed value for 6 is 4. Okay, the observed value was 4. The predicted was 3.82. So the table gives f of 6 as 4. So the regression equation underestimates the value of f of 6. Because we're supposed to be 4. By how much did it underestimate it? 4 minus 3.82. And underestimated it by 0.18. So this is not bad. And if you were to round to the nearest whole number, you'd get 4. So our model, notice that since it didn't give the exact value that the table gave, that says that the data are not exactly linear. And part D was to estimate f of 7. So if I do my f of 7, so second, enter, change the 6 to a 7, 4.60. Okay. So from the regression line, you're going to get 4.60. Notice this is a lot easier than trying to do that average rate of change stuff and then how many values between 7 and 6 and all that other nonsense we did way back in chapter 1. So there's the answer to D. The regression model predicts f of 7 to be 4.60. Okay, number 2. It says the height h of a 25-year-old male is only a function of his weight w. So notice in that setup, h is a function of w, so w is the independent variable. So the following information has been collected for 25-year-old males. Based on the information, find the equation of the regression line that gives the height h of a 25-year-old male in terms of his weight w. Then use the equation to estimate the height of a 25-year-old male that weighs 200 pounds. Round coefficients to the nearest hundredth and height to nearest whole number. Now again, the height is in inches. Okay, again, notice the problem is asking two things. Find the regression line and then use it to figure out or estimate a height of a 25-year-old male that weighs 200 pounds. So since we'll be using our regression line to do a calculation, we'll once again store it in y1. So let's get our calculator set up to do this problem. So I can clear this nonsense out. Hey, I'm going to do the rounding myself, so let me set my float back to float. And we quit this. And remember, we've got to clear out our lists. So second plus, which is the memory, and choice number 4, press enter. All my lists are clear. Okay. Now remember, we did store the previous value in y1, so if I press my y equal, it's still sitting there. You can go ahead and clear that out too. If you don't clear it out, the calculator will overwrite it when we store this one. So let's enter our data. So stat, press enter, go back to L1 for the weights. Okay, 150, enter, 170, oops, didn't have the 1, 170, enter, 165, enter, 185, enter, 160, enter. Okay, scroll to L2, 68, enter, 74, enter, 70, enter. 72, enter. 69, enter. Okay, got all my values in. So we quit that. Okay. Then we do stat, forward to calc, choice 4. Let's store the equation in y1, so vars, y vars, enter, enter, and we got it in y1, and let's calculate. Okay. So it says the coefficients to the nearest hundredth. So that's 2 places. I'm going to have y equal, not y, I'm having h, right? So h equals 0.14w plus 47.81. So again, I didn't really set my float to 2. So you enter the data using the stat key. So there. And then stat calc over to 4. Okay. We're going to store it in y1. Now again, because I did set my float to 2 when I did it in the PowerPoint, I'm getting my A is 0.14, my B is 47.1, which, we got the same thing when we rounded ourselves, 0.14, 47.81. So now again, we use the correct variables. So H is equal to 0.14W plus 47.81. And then the regression equation for a height of a 200-pound, 25-year-old male. We're going to do y1 of 200 to the nearest whole number, 76 inches, right? 75.81. In case you're wondering, 72 inches, or excuse me, is 6 feet. So 76 inches, this guy is 6'4". So that's how we can do linear regression on the calculator. Now, every time we press that calc key, you may have noticed other regression things. Something that ended in REG was some sort of regression. So there are a bunch of other types of regressions that we can use other than just linear. It's just that when you're doing it by hand, linear truly is the easiest one to calculate. That's the end of section 3.4. My mouse still won't work with me.